When a local brewer uses grass to filter omubisi to extract clear banana juice, they are putting experimental chemistry into practice. Move from the village to a formal laboratory, and you find scientists relying on the exact same principles to isolate and test new medicines. Whether at home or in a modern facility, experimental chemistry is simply the controlled process of safely separating and purifying matter. Here is a classic chemistry problem. We have a dry, complex bucket filled with sand, salt, and iron nails. We need to separate them into 3 pure, individual piles. Before we touch anything, we do a strict risk assessment. We establish our rules: no bare hands and absolutely no tasting the materials. To solve this problem without using chemical reactions, we have to exploit the distinct physical properties of each material in a highly specific sequence. We start in the dry state. A magnet extracts the iron nails from the pile, getting them out of the way. Next, we add warm water to exploit solubility. The salt dissolves entirely into the liquid, while the sand remains solid at the bottom. Now we use filtration. Pouring the mixture through a funnel physically traps the solid sand, allowing the liquid to drain through. The brown sand left on top is the residue. The clear, salty liquid that passes through the paper is the filtrate. By combining magnetism and solubility in order, we successfully isolated the iron and the sand. Now we just have the liquid solution to pull apart. If our only goal is to recover the solid salt from the filtrate, simple evaporation works perfectly. The water boils away into the air, leaving dry salt behind. However, if we need to recover pure drinking water from a salty source, like the waters of Lake Albert, we need to trap that moisture. By heating the flask in a simple distillation setup, we boil the solution and channel the rising vapor. During cooling, the vapor enters a Liebig condenser. Cold water jackets the outside, forcing the vapor back into a pure liquid called the distillate. Distillation is the required method when a problem demands the complete recovery of both the liquid solvent and the dissolved solid. So how do you scientifically prove this clear distillate is 100% pure without tasting it? You measure its temperature. A thermometer proves that pure water boils at exactly 100 degrees Celsius. If there are impurities, like an invisible pinch of salt, the liquid will boil over a fluctuating range of temperatures instead of locking on to a fixed number. In chemistry, pure does not mean visually clean. It means a substance consists of only one type of particle, confirmed by a sharp, exact boiling or melting point. To separate miscible liquids, liquids that completely mix like alcohol and water, we use a fractionating column based on differing boiling points. For dissolved dyes, paper chromatography forces the mixture up a paper strip, revealing the hidden colors that make up black ink. While the tools and glassware change, the overarching rule remains constant. Chemists identify distinct physical properties to pull any mixture apart. This flowchart maps out the process. For a solid and solid mixture, check magnetic properties first. With liquids, an insoluble solid requires filtration. A dissolved solid needs evaporation or distillation. Finally, prove your separation worked by testing for a sharp, fixed boiling or melting point. Memorizing these specific pathways and adhering to strict risk assessments will equip you to safely solve complex chemistry problems in any laboratory setting.